Welcome back. Today, we are unpacking two essential high-yield engineering systems that dictate how our physical world operates. First, we will examine railway networks. This animation shows a simple node expanding into a complex hub. Train stations aren't placed at random. They scale in physical complexity based on strict operational demands. Second, we turn to fluid mechanics. Our objective here is to find the exact mathematical condition required to transmit maximum power through a pipeline. Intuitively, you might assume that pushing a fluid faster continuously generates more power, but physics imposes a hard mathematical ceiling. Friction dictates that maximum power is achieved only when the head loss equals exactly 1/3 of the total head. Mastering these systems, knowing exactly how networks scale and where physics caps performance, is foundational for engineering exams and real-world design. Let's start with a completely empty straight railway track. This represents an uncontrolled transportation line. Looking at the text, we see the simplest node, the halt station. Just a rail-level platform with zero infrastructure, no yard, building, or staff. Its operational capability is strictly limited, accommodating only a 1 to 2 minute stop for basic passenger boarding. Upgrading the complexity brings us to the flag station. This node introduces a physical station building and dedicated staff. This allows for critical operational additions, communication tools like a telegraph or control phone, and a siding track specifically for stabling wagons. Next is the crossing station. Unlike a flag station, which only handles local traffic, a crossing station introduces the physical arrangements necessary for controlling the actual movement of trains along the line. Specifically, it provides the track mechanics to facilitate the safe crossing of trains moving in opposite directions on a single line section. Finally, we reach the most complex node, the junction station. This is defined as the meeting point of 3 or more lines emerging from different directions. At a junction, routing capabilities expand massively. Trains can arrive from branch lines and return, or proceed directly to entirely new destination networks. Railway stations operate as purely functional nodes. Each tier in the hierarchy adds specific physical infrastructure to solve a distinct traffic bottleneck. Moving to our second module, we apply this exact logic of physical constraints to fluid mechanics, transmitting power via flowing fluids through a pipeline. The power transmitted through these pipes depends on two critical factors: the rate of flow, or discharge, and the total head available at the end of the pipe. This schematic illustrates the physical model used to derive these mechanics: a standard tank connected to linear pipe AB. The core variables are total head, capital H, at the inlet, and the friction factor, H sub F, which causes head loss. Because of this friction against the pipe walls, the actual effective head available at the pipe's outlet is reduced to H minus H sub F. Looking at this block of equations, we start with the standard base formula for power, P. It is derived from the specific weight of the fluid, the discharge, Q, and the net head. To solve for the variables we control, we substitute discharge Q, replacing it with the cross-sectional area of the pipe multiplied by the fluid's velocity. This yields the fully assembled algebraic equation for power transmitted at the outlet. This equation accurately models physical reality. It gives us the exact mathematical foundation needed to calculate the system's absolute limits. To optimize this system, we turn to calculus. Finding a maximum requires differentiating the power function with respect to its changing variable and equating it to 0. Here, fluid velocity, v, is the variable we differentiate against, setting the derivative to 0. The first step isolates constant terms, like density, gravity, and area, pulling them outside the derivative bracket. Note that the head loss term, H sub F, is substituted with its full Darcy-Weisbach equivalent formula. Now the entire expression inside the bracket is defined entirely in terms of velocity. Executing the differentiation, the h times v term simply differentiates to h. For the second part, the v cubed term inside the friction component differentiates to 3v squared, giving us this updated equation. We can simplify this by recognizing that the complex fraction remaining inside the bracket is exactly equal to our original friction term, h sub f. That substitution leaves us with a clean, simplified equation, h minus 3h sub f equals 0. Rearranging this final formula reveals the ultimate engineering constraint. Maximum power occurs exactly when h sub f equals h over 3. Nature enforces a strict penalty. Push a fluid too fast, and friction mathematically consumes those gains the moment you exceed that 1/3 threshold. All physical engineering systems operate on a knife edge of efficiency, control, and mathematical limits. In the railway module, we saw that infrastructure physically scales in exact proportion to routing demands, expanding from a bare concrete halt to a highly controlled junction. In hydraulics, physics prevents infinite scaling. Velocity cannot just be increased blindly. A system hits its absolute maximum power capacity right at the point where friction consumes exactly 1/3 of the total available head. This exact derivation dictates the real-world design of massive infrastructure, calculating the precise limits for hydroelectric penstocks and industrial turbine intakes. Mastering these exact constraints, knowing both how to build a system up and exactly where physics will shut it down, is the hallmark of an elite engineer.